Well, hello everyone. Welcome to Zomboland Gaming, but it's not gaming, but it's going to be concerning a game. So, today we are going to cover a topic that I probably should have started before I started the last video game series that we started. That was a whole lot of the use of the word started. So, as we did the first two episodes of Turing Complete, which by the time you watch this video, I don't think the second episode will have come out yet, which is actually going to be beneficial. But anyway, so as I was going through this game, which we're actually going to watch the trailer together because, I really would like you guys to see this game. It's on Steam. It is what? Well, of course, it's not going to... Oh, yeah, right there. What is that? $19.99? So $20. I actually think I bought it on sale, so I think I bought it for a little bit cheaper. So waiting for sale would not be a bad idea, but it's not a bad price either. So let's go ahead and we'll watch this trailer. Oh, we turn some sound on. I don't even know if it has sound. A humble start with nothing given. In to out. With an OT gate in it. Create every component yourself. Level complete. That was an half adder, by the way. Build more complex circuits. Not really sure what that component is. I haven't unlocked it yet. Eventually complete your first computer. Yes, so this is what we're going to be creating. This is the whole point of that game, by the way. Programming in binary is a pain. Yes, it is. And this, for anybody who plays Minecraft and has ever made a redstone computer, that's what you're doing. You're having to put torches down to signify every part of your program. But so look, this is all that we're going to be doing with this game. We're going to be able to create a video game in a video game with a computer that we created in a video game and the programming inside a video game. Woo-hoo-hoo! So anyway, so this is giving you an idea of that game that we just played, right? So Turing Complete, it's available on Steam. But as I discussed in that game, there was a lot of things about it that I didn't like the way that they presented the information. So for somebody who has no understanding of logic gates, binary, blah, 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 you were going to really struggle to understand how to complete each one of the tasks given and eventually build a computer right. You might get there, but the likelihood that you'll understand how you got there is going to be, pretty low. So I decided to make not a spreadsheet. This isn't a spreadsheet. This is a slideshow. So I have this wonderful book right here, Practical Electronics for Inventors. It is by Paul Schurz and Simon Monk. I've owned this book for a long time now. I've also, I went through different college classes where I used various forms of things like this. I was in the nuclear Navy and had to do Boolean logic and a couple other electronics classes within the Navy nuclear power program. And so, I have a semi-decent understanding of a lot of this. Surprisingly enough, 20 years ago, when I went through all the nuclear power program, I kind of forgot most of it until 2010, as I discussed in one of the videos earlier. That Minecraft kind of reintroduced this love of digital electronics to me, just because of Redstone. And so I started tinkering around with breadboard circuitry and making like little NE55 timer synthesizers and making a working 8-bit computer all in discrete logic gates on a breadboard, things like that. And I had to go back and I had to read through books like this and a bunch of other books, break out my old applied engineering books from the Navy. And so I think this is going to help, right? So not only is this going to be for people who are just interested in digital theory, it'll help out for redstone circuits in Minecraft. It'll help for making breadboard computers, but then also like understanding how all of this works, all of how everything in here works, how your Super Nintendo Entertainment System, how your PlayStation works, how your car stereo works, like all that sort of stuff, right? We're solely going to be focusing on just the digital side of it, the IC chips, the little logic gates, the transistors, the clock circuits, all that stuff, right? And we got to start at the very basics. So this is going to be day one, digital electronics, and the intro for this will be a whole lot shorter from now on, but I had to kind of discuss what we're going to be doing here. So this is going to tie in with the Turing Complete game. I'm going to be putting out kind of side by side, probably a episode of this and an episode of Turing Complete, kind of to make them coincide a bit. But so, digital electronics, the basics of digital electronics. Analog versus digital. So far, if you've known anything about electricity, when you plug your phone charger into a wall, you plug your computer into your surge protector, your oven, your washer and dryer, all those sort of things are using your 120 volt power supply in your house, which is AC, alternating current. The top graph here is display of one phase of an alternating current. Basically, your power reverses. So you go forward and go backwards, and what ends up happening is it's not a steady flow of power. You ramp up, ramp down, ramp up, ramp down, ramp up, ramp down. So you get the signal that's a sine wave. If you listen to synthesizer music, any EDM, techno, stuff like that, that is a synthesizer, which is a sine wave for a sound that then turns into whatever the heck somebody's manipulated that sine wave to sound like. Whereas in DC circuitry, so think of a battery or anything that's an IC chip on a computer, or if you've ever worked with any kind of like photoelectronic sensors or things of that nature, it's going to use DC voltage, direct current voltage. So that's just going in one direction, positive to negative. And so what that ends up doing for a digital circuitry is that we don't care about the in-between points of the voltage so much for signals. We just look at, is full power on, is full power off. There are going to be some examples later on down the road when we start actually building components and whatnot that you're going to see some of these circuitry require like a high voltage of 3.3 to 5 or a low voltage of 0 to 0.8 or something like that. But for the simplified version of what a analog versus digital signal is that analog has a positive and a minus voltage. Digital is 0 for low voltage. 5 voltage normally, or some level of voltage is the high, and it's either off or it's on. So that's what this chart is representing. The digital logic only has 2 voltage states, right? It's high or low, on or off. As we're going to see down here, 1 or 0. So this may represent an off state, so inside that logic gates, like I believe I said in the Turing Complete videos, transistors. Little tiny ass transistors make up all of the components inside all your circuit boards and everything, and those transistors have to turn on and off based on a certain voltage going through them. So that's the on and off switching of a transistor. Or if you think of a light switch, right, you turn the light switch on or off. Your light is either on or it's off. If you put a dimmer switch in there, that's a different scenario, but just a basic light switch on off, right? And it's one bit of information. So as we're going to see as we build this information up, each line of power is going to be one bit of information. High and low state. So it can represent a true or false statement. So this comes into play when you start programming. If you've gone into any kind of like JavaScript or not JavaScript, but Java programming for say Minecraft or Ark Survival Evolved, server settings, Scum server settings, things like that, you'll notice that you'll have some sort of statement and you'll put true or false behind it. And that basically means true, turn this thing on, enable this thing. False, disable this thing. Well, it's similar for Boolean logic. True is going to be the high state, false is going to be the low state. 1, which is on, 0, which is off. Not always the case. It's kind of the choice of the person that's designing the circuit. But if they're designing the circuit, they will state whether a low state is your true and a high state is your false, or vice versa. They'll have to state that in the schematic. But for the most part, most of the things you're going to look at are always going to be the thing is true / enabled if it's high. The thing is false / low / 0 if it's if it's that way. Like I put down here, to get around that, some designers will say positive true, which means that the high is a true statement, or negative true, which means the high is a false statement, just to help avoid any kind of confusion, but not always. So in Boolean, it's a 2's base system. So we only have 2 numbers, 1 and 0, which is why it's called 2's base, or base 2. So 1 is usually equal to true, 0 is equal to false. In electronics, however, though, so that's just in Boolean, that's just the expression, the way that we show what the circuit is trying to do. But when you look at a schematic, that's not reading out the Boolean number. That's typically going to read the voltage state of whatever the component in the computer is doing. So 1 would be the high voltage, 0 would be the low voltage. And then, like I said, it's generally 5 volts for most components and 0 for the off state most of the time. So here's some of the different number codes that are used within digital electronics. So you got decimal. We all know what decimal is. It's called a base 10 system because you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 numbers, right? and hence the 10 to the n power, or 10 to the n. So binary just uses 2, so it's just 1 and 0. And then we also have what's called octal and hexadecimal, and octal, oct meaning 8, hex meaning 10. So in octal, you have 0, 1, 2, 3, 4, 5, 6, 7. That gives you 8 numbers. In hexadecimal, we go all the way through 9, and then, oh crap, we're out of numbers, because I don't want to do 10, because 10 is 1 and 0. I already have a 1 and 0. So we add A, B, C, D, E, F, right? So A being 10, B being 11, C being 12, D being 13, E being 14, and F being 15. 0 through 15 makes 16 numbers. Hexadecimal. Sorry, did I say hexadecimal is 10? It's 16. Why did I say 10? Hexadecimal is 10. 16! God, words! Words are tough. Words are hard. Octal 8, hex 16. Get that in here. Woo! All right, and then for last, we have binary coded decimal, which there's a difference between binary 2 decimal and binary coded decimal. And we'll get on this topic later on down in the slides, but basically it's just a system that you can take each individual number and separate it out into 3. So like 1 would be 0, 0, 1. 3 would be 0, 1, 1. So you can separate out a bigger number into similar parts. It makes it easier for a machine to like put out to like a 7-segment display, stuff like that. So here's an example, right? So in decimal, 736 with a subscript 10, showing that it's a base 10 number, showing us that it's for decimal. The way that you would write it out in long form would be 7 times 10 to the 2 power, because 7 is in the 2, in the, the 10 to the 2's place, or hundreds. 3 times 10 to the 1, or the 10's place. 6 times 10 to the 0, or the 1's place. Because, 1 to the 0 is 1, 1 to the 2 is 1, 1 to the 2 is 3. Why am I using 1 as an example? That doesn't really work very well. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100. So there we go. All right, so binary, the way we would write this number in binary, right? Not 736. This is a different number. I probably should have wrote the decimal form of the number down below, but we're going to get into decimal to binary later. So this right here is going to be 12, 16, so that's 28 in binary. So what that equals in long form is 1 times 2 to the 4, 1 times 2 to the 3, 1 times 2 to the 2, 0 times 2 to the 1, 0 times 2 to the 0. Just in long form. Just showing that the first one is in the 2 to the 4's place, or the 16, because 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, because it's 2 times 2 times 2, 2 to the 4 is 2 times 2 times 2 times 2, which is 16. So that just shows you that the 2 subscript is binary. It's probably a long explanation that I did not need to do there, but especially because I just wrote down below. The subscript tells which system is being used. 10 for decimal, 2 for binary. And in binary, and actually in decimal really either, right? So any number, when you're looking at it, typically the way it's written, the number on the far left is going to be the highest bit of the number. The number on the far right is going to be the lowest bit of the number. The hundreds place, tens place, ones place. In this case, the 16s place, the 18s, the 4, the 2, and the 1. So that's going to become important when we start to build up a circuitry later and have bus work and things like that. We want to know what's the most significant bit and what's the least significant bit. Most being on the left, least being on the right. So from right to left, adding bits equals, sorry. To get the number right, if you just have this in front of you, if you just had 0 times 2 to the 3 plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0, if you just add those all up, then you're going to get whatever your decimal is supposed to be. So if you go 1 times 2 to the 2, that's 4. Because everything else is 0, it's going to equal 0. So 0 times 2 to the 3 is 0, plus 1 times 2 to the 2 is 4, plus 0 times 2 to the 1 is 0, 0 plus 4 plus 0 is 4, plus 0 times 2 to the 0, which is another 0, it's still 4, right? So bits, we haven't really discussed what bits are, other than each one of these numbers individually is a bit, and increasing in 2 to the n power every time we go up. So most of the things that you would ever have heard of, like when you think of video game consoles or the processing power of your computer, like, when you get Windows 10, did you get the 32-bit Windows 10 system or the 64-bit Windows 10 system? And all that's saying is, simplified, how many lines your computer have to utilize to do certain functions within inside a computer. The more bits you have, the bigger piece of information you can send to your computer to do whatever function it needs to do. Add, subtract, multiply, divide, go to the register, go to your RAM, go to your program counter, go to an addresser, somewhere, that sort of thing. And some examples that I put down here for us gamers. The NES system, the original Nintendo system, was an 8-bit system. The Super Nintendo Entertainment System doubled that to 16. The Sega Genesis was also a 16-bit system. However, with the little CD-ROM thing that you could also, it was actually 32-bit system, so kind of, PlayStation, the original PlayStation, was a 32-bit system, and then the Nintendo 64, 64-bit system, hence why it was called Nintendo 64. All right, so now we're going to get into our first kind of conversioning points, right? Because, just because we know what decimal and binary and octal and hexadecimal and BCD are, we need to know how to convert between them all. Most of them are relatively simple to do. So decimal to binary, all you're going to do is you're just going to take the number that's in decimal, divide it by 2. And when you divide any of these numbers by 2, you're either going to have 0 remainder because the number will evenly divide by 2, or you're going to be left with a 1. And so what you're going to do is you start with the first division, right? And then when you divide it, that's going to be your lowest number, the rightmost number. And then if you have a remainder, you put a 1. You don't carry that 1 over to the next portion. You just take the number that you got divided, and that's going to be your next division by 2. And then you just keep carrying down the 1s and the 0s. And then once you get it all done, from top to bottom, you just write all those numbers in order, bottom being on the left, top being on the right, and just boop, pop it down, and there you go. And here's an example of it. So 213 in decimal, hence by the base 10. We go 213 divided by 2 equals 106. We get a remainder of 1, and that's going to be our least significant bit. 106 divided by 2 is 53. We got no remainder. 53 divided by 2, 26, blah, blah, blah. You can see the whole way down, right? So once we get done, we start with this bottom bit here on the left, and it's 1, 1, 0, 1, 0, 1, 0, 1. Which is 8 bits of information, fortunately, which is kind of cool. If you don't have, like, say it's a 4-bit system and you only have 3 numbers after your division, you just put a 0 to the left side. You'll add a 0 to the most significant bits until you get whatever bit count that you need. So if you're a 16-bit system, you would add 8 more zeros to the left side of this equation just to get your full 16 bits. But it's not necessary when you just want to look at it. And to verify that this is correct, we can use the next step, which is going to be a whole different number because I wanted to show different variations of numbers. But I'm going to tell you now with this one, if you look at it here, we got a 1 because it's in the 1's place. We got a 1 in the 4's place, so 1 plus 1 is 5. And then we've got a 1 in the 16th place, so that's 21. And then we got a 1 in the 64th place, which now I'm starting to have to do math, the 85. And then we've got a, I didn't do that right, did I? Oh, yeah, 85. Plus 128, 128 plus 85 is going to be 213. Oh, God, I didn't realize I was going to have to be doing math in this. So it checks out. So now going the opposite direction, binary back to decimal. Remember, most significant bit, MSB, is on the left. Least significant bit is on the right. So you're going to expand it out. So you're going to take that 11110101, whatever the number is in binary, and you're going to expand it out like we saw before, where it's that number times whatever 2 to whatever power it happens to be, whatever place it happens to be in. You start from the right side is going to be 2 to the 0. Working your way to the left, just 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, so on and so forth until you get to your last number, and then you just sum them all together. So looking at an example here, we've got 1, 3, 8, 16, so that's 19, plus 32 is, I'm just going to look at the bottom, 187. This is 187 in binary. So if we split it all out, right, most significant bit, we're going to have, it's an 8-bit number, so 0, 1, 2, 3, 4, 5, 6, 7. So all we're going to do, starting off from this least significant bit, 1 times 2 to the 0 is 1, 1 times 2 to the 1 is 2, 0, 0 times 2 to the 3 is not 8 and 8. Did I miss a number? Hey, go back! Go back! How do I go back? There we go. I mistyped here. There shouldn't be an 8 here. That should be 0. I ignore the 8. That should be 0. Like, I'm going to put the pointer here so it looks like a 0 now. Would you stop going forward? And then 1 times 2 to the 4 is 16. 1 times 2 to the 5 is 32. You can kind of see how this is working here. And then we'll just add them all together, which my number is going to be wrong. That's not 187. That's actually 179 or 178 in binary. I have given you wrong information. I will correct this slide and reintroduce it in. It's going to be 178, though, because there shouldn't be a 179. I was right the first time. Minus 8. This is fucking confusing. I am confusing you, aren't I? So it's 179 because the 8 shouldn't be there. But you can kind of see the process, right? That's the main point. My math is wrong. The process is right. If I was to put a 1 in this 8 spot, then it would be right. All right, so now moving on to Octal Systems. Enough of my floundering with math. Octal is a base 8 system, hence the term oct. And so it's 0, 1, 2, 3, 4, 5, 6, and 7. And those are all the numbers we're going to be using. What this does is it'll take a binary number, and then say you have 6 bits of binary, it'll spread it out. The first 3, and then the second 3. If you have more, like say you have an 8-bit system, it'll be the first 3, the second set of 3, and then you'll add a 0 onto the end to get 9, and then they'll spread it out. And so what this does is it allows us to make a smaller number to transfer through our system. It's not really used, like I put here, it's not really used anymore. It was used for older systems back when we were, first really starting out with computers and whatnot. The division was a little bit different on those computers as far as how the programs utilized all the bits moving around. So it's not really used, but it's beneficial to know because you can use it. So here's a way to do it, right? So octal to binary. And then you just go in the opposite order to go from binary back to octal. So if we start with a number here, this is going to be the octal number, 537, with a base number 8. All you do is you separate it out. 5 by itself, 3 by itself, 7 by itself. And then you make the binary for each one of those numbers. So binary for 7 is 111. Binary for 3 is 011. Binary for 5 is 101. And then you just squish them back together again, and there you go. You got your binary number. And then it would just go the opposite way. If you're going from binary, you split it into groups of 3, make whatever that binary number is in decimal, put them back together again. There you go. You got your octal answer. And hexadecimal is a 16-base system, hence the term hex. So it's, like I said before, 0 through 9, and then you add A through F to it. And instead of 3, it's going to work exactly like octal does, but instead of groups of 3, you'll use groups of 4, which is really great because most of our systems nowadays are going to be 4-bit, 8-bit, 16-bit, 32-bit, 64-bit, all those things that are greatly divisible by groups of 4. And so in the case of like where you can see here, and most likely if you've ever used, say like an Arduino or any kind of matrixing systems, it'll take that big number that you just really don't want a whole bunch of these big numbers and squish it down into a hex number, which usually you can take an 8 down to a 2-bit number with hex, and that way you can shorten all your information out. So it works exactly the same, like I said, as octal to binary and vice versa. So in this case right here, we've got 3E9. So A, B, C, D, E. That's 10, 11, 12, 13, 14. So it's 3, 14, and then a 9, right? That's what we got here. So if we look down here, 0, 0, 1, 1 is 3. 9 is 8 plus 1 makes 9. And then we've got 8 plus 4 makes 12 plus 13. Did I? 10, 11, 12, 13. A, B, C, E. That's a 2. Good Lord, what is wrong with me in math tonight? 8 plus 4 is 12, plus 2 is 14. Good grief, me and math don't get along. And then, of course, you just squish that back together again to get the number on the bottom, and then reverse it. Break the binary into groups of 4, separate it out into the decimal form, squish it back together again, add the little 16 at the end, you know it's hex. Don't let me do math. Just never let me do math. So the final numbering system is called binary coded decimal. The only time you're really going to see this is with like display circuitry. It's just a way for the computer machine code to transfer information a little bit easier. So like I put here, outputs to the digital display. It represents the language of the machine code, not the programming code, not the binary within the machine, but the actual machine code for doing functions. And it's represented as a 4-bit binary number. And then it's rarely ever calculated just because it's kind of a mess to calculate. But here we go. So here's BCD. So a BCD is a 10-base system, and it's using 150. So 10 we know is decimal, right? So it's a decimal number, hence the 10. All you do is you separate it out, 150, just like we did with the octal and the hex. When we separate those numbers out, we just represent that binary here. And so 0 becomes 4 zeros, 5 becomes 0, 1, 0, 1, 1 becomes all zeros with a 1 at the end. And that's our BCD. And then converting it it's a little bit different. If you want me to go in real detail on converting BCD, we can. I've done some stuff in Minecraft as well that I can show some good examples of it. But I'm not going to go into it. It's a pain in the butt. Most of the time, you can just literally go, what's the binary? Turn it into decimal. I'm done. But you really rarely ever need to calculate it out. So we're going to skip that. All right. We haven't talked about negative numbers yet. All we've talked about is positive numbers. 0 through 9 and 0 through F, right? We haven't talked about any negative numbers. So computers add. For the most part, if you build any kind of components in a computer, all it is doing is adding. So to get a negative number, you have to subtract. There's no other way to get a negative number other than subtracting. Unless we start talking about multiplication, divisions, and things like that, right? But even then, those require a negative number to get to a negative number. So the way this works is there's two methods. One is called sign magnitude representation, and it's simple, it works, but it struggles to do subtraction, so it's rarely used anymore. There's a thing called 2's complement, which we'll see in the next slide, is what's going to be popular and used most of the time. But just to discuss it, because you can utilize it in some cases, sign magnitude representation. So you take the leftmost bit and you reserve it as what's going to give you the minus sign in decimal, or not give you a minus sign, which would then clue you in that it's a positive number. So that most significant bit won't be able to be utilized. So say you have an 8-bit system, that last bit is going to be number 128. Well, now you no longer have a 128th bit, so you're only adding 121. You can only get max the number 121 because this bit cannot be added anymore. And so the way it works is if it's a 0, then you know the number is going to be positive. It'll be a positive 121. If it's a 1, then the number will be negative 121 because it'll put a little negative sign in there. Really not used for arithmetic. I don't know if I don't show an example in this. I can. If you guys want me to show an example, I can. But it's rarely ever used in arithmetic functions. It's mainly just for displaying numbers, just to give you that minus sign on a display without having to do something else for your display to show that negative sign. So we'll move on from that. This is the one that we're always going to use from this point forward. 2's complement. So it's a much better way to deal with negative numbers. And basically what it does, in simple terms, is it takes whatever your binary number is, which we will call the true binary number, and it just takes all the 1s and 0s and flips them to the opposite. So if you got a 1, it turns to a 0. You got a 0, it turns to a 1. And then we basically add them together. So, for addition or whatnot, right? And so if you flip the number and add it to the original number, all of them should go to 0. Should. But there is an extra step, and you got to add a 1 to it, as we're going to see. So if the decimal is a positive number, the 2's complement number is just going to be exactly whatever the binary number was. So if you take your decimal, convert it to binary, if it's positive, just leave it alone. You're done. So in the case of the example I have down here, I have 41 in decimal. I hope I did my math right, because as we've seen, I'm terrible at freaking math today. So if you got positive 41, and we break this into binary, then we've got a 32. Is that 32? That's 32. 32 plus 8 makes 40. Plus the extra 1 is 41. Yes, I did math. Woohoo! And then the 2's complement of that is nothing. We don't have to do anything. It's going to be the exact same because it's a positive number. So if the decimal is negative, however, you got some extra steps. So you take the decimal number, make it the binary of that decimal number, then you invert all of it, which is called the 1's complement. So all the 1s go to 0s, all the 0s go to 1. So then that new number is called the 1's complement, and then you're going to add a 1 to the least significant bit. So you're basically adding the number plus 1 bit. And then that new number is going to be your 2's complement. And that last bit is going to be your sine bit. And if it's a 1, because it should always be a 1 if you're adding, if you're converting negative numbers, then that will let you know because it's your sine bit. Your sine bit is telling you, yep, you're a negative number. And so here's an example of that. So we've got negative 41. I actually, for once, used a similar example. So here we go. Binary for 41 is the 16-bit, or sorry, 32-bit, the 8-bit, which makes 40, and the 1-bit, which makes 41. True's complement, as you can see, the zeros turn to ones, the ones turn to zeros the whole way through. And now we're going to add 1 to this last bit here. And so we get a 1 where there was a 0, and the rest of it stays the same. So this is the 2's complement for negative 41. It's going to read out looking like it's whatever number that is because me and math are not getting along today. So I'm not even going to attempt to add it. I probably should have shown it here. But this suffices. We know that this is the opposite of this. We know we've added 1 to the least significant bit, giving us a 1 in the last place. We know that it's a negative number now. You really won't have to do this too often, but it will come in handy when you try to reduce circuitry and figure out how to utilize your circuits the way you want to. So 2's complement to decimal. So going backwards. So it's not as simple as just going backwards, right? So if the 2's complement, that sine bit, that least significant bit is a 0, then we know it's a positive number. Just go ahead and convert that binary number right into decimal. If it's a 1, however, you know it's going to be negative. So complement all the bits. So take that number that you got, the true binary. Well, not really true binary because it's not true binary yet. Take that binary number that you have, flip all the bits. So all the 1s go to zeros, all the zeros go to 1s. Then add a 1 to the least significant bit, which should take that last place 1, convert it to a 0. Then do binary to decimal after that point. Because now you've got your true binary. And then all you have to do is convert that binary to decimal. And then add the little negative symbol in front. So here we go. Here's an example of this. So this is our 2's complement number. We know we've got the 1 here. So we know that it's going to be a negative number. When we flip it around, we got 1s go to zeros. Zeros go to 1s the whole way through. We're adding a 1 to this least significant bit. And then if we go here, we got 1 plus 2 makes 3. Plus 8, 16. 3 plus 16 is 19. Plus 32 is 51. And then we just add the little negative number here because we have, we knew it was a negative number. Fairly straightforward and simple. So now we're going to get into arithmetic, specifically just adding and subtracting. Multiplication and division is basically just doing more adding and subtracting in order to get it to multiply/divide. That's really all a computer does. A computer pretty much by itself only adds, because as we saw with the negative number, it's just an adder. We just flipped some stuff in order to get us a negative number. We just told us put a negative sign here. We didn't actually do any subtraction. So your computer pretty much only adds, and through that and through other circuitry, it enables itself to do a whole bunch of other stuff. So we'll get into multiplication and division later. So adding is like adding in decimal. In the old school form, you put a number on top of a number and you go from right to left, this number added with the number below it. And if it's greater than 10, then you have to carry that first highest bit over to the next column. So on and so forth. Same way here. We only have 1s and 0s, but a 1 plus a 1 gets a 2. Well, I don't have a 2 because it's not available to me. So I would put a 0 down below and add a 1 to the next leftmost column. Add those numbers up together, and if it ends up being 2 again, you put a 1, add a 1. If it's, 1 on the remainder with a 1 plus a 1, well, that makes 3. So I would put a 0 and it'd be a 1 down below, because, I'd get a 1 there, and then my 2 would carry over to the 1. Kind of confusing, but we'll kind of see it in the next slide of what I'm talking about here. So we're going to add 5 plus 3 in decimal, which is 8, right? We're going to go back to grade school here. So what you see here is, here's my 5 in decimal, written out in binary, which is 0101. We've got our 3, which is 0011. So we're going to start with the rightmost column, the least significant bit. 1 plus 1 makes 2. Well, I can't have a 2, So I put a 0 here, and I add this little red one up at top. So now it's 1 plus 1 plus 0, which is going to give me 0 and a 1, because that's 2. And then we've got 1 plus 1 makes 2 again, plus 0, still 2. So we get a 0, put our 1 over, and then 1 plus 0 makes 1. Just like old grade school math. Now, subtracting is a little bit different, right? So if the top number is smaller than the bottom in regular decimal, right, you would borrow from the left one, you know, because it's a tens place. So you borrow it, reduce the number for that column, and then you add a 1 over to the right bit that you're trying to, you know, reduce from. So that way you get a bigger number, right? You basically have made it now a tens. And so that doesn't work with here at all whatsoever. You can do it, but you can do it out on paper in long form. It's messy. We're not even gonna get into it. I told you here that says you must borrow a 10, which is 2 to the 10 subscript there, but not even gonna deal with it. We're not even gonna deal with it. We're just gonna use 2's complement. So basically all you do here, we're gonna use my example of 19 minus 7, which equals 12. So the first number you're gonna keep as a positive number. So 19 in binary is 0001, 0011. I put it as an 8-bit number just to make things look clean. But basically, it's 16 plus 3 makes 19. The second number, we know is negative because we're subtracting. So we're reducing that number. We're going to use a negative number. So you take the true, we're just going to basically, negative number 2's complement this out. So the true binary is the 3 ones to equal 7. Flip all the bits. So now all the zeros are ones and all the ones are zeros. Add this number 1 to the final column here. And now you're going to get all the ones minus these 2 zeros with the 1 at the end. And now you're basically just gonna add those 2 numbers back together. I love slideshows when you keep, missing all your slides. There we go. So now all you're gonna do from this point on, even though it's a negative number, you're just gonna add them. So then we just go back to basic, the slide before where we were adding. So 1 plus 1 makes 0. We carry the 1. The carried 1 plus 1 makes 0 with a carry over, which 0 plus the carry 1 makes 1. There's no carry this time, so 0 plus 1 makes 1. 1 plus 1 makes 2, so we got a 0 with a carry. 1 plus 1 makes 2, so it's a carry, and it just carries all the way over to where technically we should have another bit here. It's going to be a carry out of 1 that's not on a... We don't have a 9th bit to put this 1 on, so it would go to like a flag or a carry out or something else, but it would be there. So in this case, 8 plus 4 in binary is decimal 12. There we go. And then this is the final thing that we're going to talk about. So Ascii. We, as making computer chip people and all that sort of stuff, aren't really going to deal with Ascii. This is more on the programming side of things, but you can also put it into your machine code so it just knows. So it stands for American Standard Code for Information Interchange. Like in the case of where I work currently, we have a bunch of barcodes that are 8-digit barcodes that are in decimal. They're 8 digits of decimal. And so what ends up coming through the barcode reader scans it, turns it into binary, and then turns that into Ascii, and then it sends it up to a matrix on a upper network system, and then it looks up in the matrix for, is this barcode a legitimate piece of information? If so, send that back saying, yep, you're good to go. So the other thing that most people use for, especially if you've ever been on 4chan or Reddit or any other comment post and you've seen people make the stuff out of tanks, like they'll make tanks or little anime figurines or boobages, and they're using the letters and symbols on a keyboard. That is all Ascii, right? So that's what it's used for. It's an alphanumeric code used to transmit between computers and peripherals. So the letters, the symbols, the numbers, and then other characters that are non-printable characters like your function keys and things like that. So it's 128 different 7-bit codes. So in the case of this, 0000000, which is the 7 numbers there at 7 bits, because remember, each one of these is a bit. So 1, 2, 3, 4, 5, 6, 7 bits of information. Or this is the first time you're going to see hex. 00 in hex right here is the same number as this. Or 0011111, which is 16 plus 8, 22, 24, caught myself, 28, 29, 30, right? 30, that's wrong. That is the wrong number. Just don't listen to me doing math. Just 15 plus 1 is 16. Oh my God, Nathan, I'm just dumb. I'm just dumb today. I am absolutely dumb today. Just don't listen to me. So anyway, that number, the code 0011111. See, even if you know all this stuff, you still screw it up big time. It's used for non-printing characters specifically and special machine commands specifically. It's not used for anything else other than these things. So non-printing characters being your function keys, or, you know, if you've assigned something on a keyboard that does something else, right, but it's not going to actually display on something, that's the non-printing characters. And then if special machine commands would be like the escape, the delete, the character turns, anything that flags, stops a program, interrupts a program. Interrupts is the better word to use for it. Things like that. That's what these are going to be used for. And then the rest of them, so 0, 1, 0, 0, 0, 0, all the way up through everything being ones, is going to be reserved for the printing characters. So anything on your keyboard that when you type it, it puts it up in Notepad, Excel, any of that sort of stuff. That's these. That's all your printing characters. So I put down here, it's just ascii-code.com. That's the full list of all the current usable ASCII commands, and that you can actually go, and that way you'll be able to type in ASCII like on any kind of program. It's typically an 8-bit system. So what they'll do, right, is it's a 7-bit code, but most of our stuff runs on 8-bit kind of systems. So they'll put that last bit as either 0 to just ignore what's going on, or a 1 to say, I need to make sure that this is actually right, or I want you to add something else to this as well by, you know, going to a different code or some other sort of function along with it. But there we go. So that's the full list of ASCII. So I know this is a whole hell of a lot of information, but we're done. Woo! That's lesson number 1. The rest of these are going to be relatively short because we're just going to cover one little topic at a time from this point on. The basic logic gates, we're just going to go through and, NAND, NOR, OR, NOT, exclusive OR, those kind of things. We're just going to go through the basic logic gates next time, and then we'll start moving into combinational logic. And the combinational logic, we're pretty much just going to stick with one small little topic each lesson, just so I don't overload you. They'll probably only be 10, 15 minutes long from this point on. But this gets all the basics out of the way. So now when you go to play Turing Complete, or you go to build a redstone circuit or whatnot, you at least can understand what the hell binary even is. Hopefully. If I didn't present something in a proper manner, or I didn't quite say something that was computable in your brain, definitely leave a comment below, and if I have to, I'll come back in and revise stuff. But at least the slideshow, I can also, you know, this is a slideshow saved on my computer, so if you guys want this, I can email it out to you guys. So just, you know, private message me, and I can get this sent off to you, so you can have it. And we've got a lot to cover. There is a lot about digital stuff, a lot. And so we're even going to show examples of this in like Minecraft. I'm going to bring up Minecraft, and I'll make some redstone circuits based on real life stuff in Minecraft. You know, I can use like in Rust. I can do the electronics in Rust, or, you know, we'll play around with it. We'll even get to the point with Turing Complete. You're going to see a lot of this inside Turing Complete as well. So anyway, whew, this lesson is done. It's been a long one. I hope you guys learned some stuff. I hope my poor math, I can't even word, I'm so struggling with math. It was, you at least got the process. At least you understood what the process was, despite my inability to, you know, count simple numbers. So I hope you guys enjoyed. Don't forget to hit like, subscribe, comment, and I'll see you guys in the next one, which is going to be Satisfactory. Then it'll be another Turing Complete, and then it'll be another one of these. So see you guys next time. Ta-ta for now. Bye.